So this is E658 lecture 34. So last time around we were looking at current steering DACs. So the basic idea is, depending on which one of these guys is high, the tail current I is steered either towards the left or the right, and depending on how you want to implement your DAC. I mean, if you want to do a binary weighted design, then you copy and paste this twice to get the next significant bit, copy and paste 4 times to get the next significant bit, and so on, and you just join the output nodes, because current summation is simply done using Kirchhoff's current law. Now let's see what all, I mean, as you would probably expect, there are more things to this than meet the eye, right? And let's see what all can go wrong and see what we need to do to fix all the problems. The first thing, of course, is that you want to look at what happens if everything in this diagram is not ideal. So the only ideal element here seems to be the current source. The first thing to think about is what happens when the current source is not ideal. What is the what all do you need to make sure that this guy here behaves like a current source? This is going to be implemented, we know, with a transistor operating in the saturation region. So what do you think, what all should I make sure of to ensure that this guy behaves like a current source? So the first thing to ensure is that this transistor must be in saturation, and let's now figure out, even if M1 is in saturation, what happens in practice. You know that the I versus V characteristics are basically something like this. So the slope is not zero. There's a finite, there's a non-zero slope corresponding to the output conductance of the transistor. This non-zero slope will cause finite output impedance of the current source. Let's see what happens if there is finite output impedance. In other words, the output voltage, the first non-ideality that we would like to examine is finite output impedance of the current source. If you had an n-bit DAC and the digital code was M, digital input code in decimal form was M, then what do you expect? The equivalent model is the following. The output, this is VDD. As we saw yesterday, we are interested in differential DACs. So this is one set of guys, and this is the other output. On one side there will be approximately 2 to the n minus m times I. On the other side there will be, see how many guys are we steering to the right and how many are we steering to the left. There are m currents. If you consider a fully thermometer DAC, then if the digital input code is m, the output current must be proportional to, right? So if m of these current sources are steered to one side, it follows that 2 to the power n minus m current sources are steered towards to the left. This is what you would expect in practice. So the differential output is nothing but VDD minus 2 to the n minus m times I times RL minus VDD minus m times IRL. It is 2mi times RL minus 2 to the n I times RL. So if m is 0, then the output will be minus 2 to the n times I times RL. If m is equal to 2 to the n, then the output will be plus 2 to the n times I times RL. So, I mean it's differential, so the output must go from minus something to plus something. Now, in practice, what happens, each of these current sources is not ideal. So, if m current sources are steered towards the right, in practice what do you think will happen? To account for finite output impedance, what must I do? Put a resistor in parallel or a conductance in parallel. What is the equivalent conductance? Assuming the output conductance of one current source is GO, this will be m times GO, and this will be 2 to the n minus m times GO. So, can you comment on the correctness of this model? Is this, I mean, why is this model correct? All right, I'll show you that it's not as correct as you might think. See, for an ideal current source, this is what I versus V should be. Now, what we actually get is something like this. Okay, so this is ideal and this is actual. If you are interested in this region, that is, I'm going to tell you that I will assure you that none of the transistors get into the triode region. So, you are basically interested in the region drawn, you hope that the DAC will, all the transistors will only operate in that region. So, what is the, so now can you comment on whether the model is correct or wrong? One objection of course is that we are all in the, you can't use a small signal linear equivalent circuit that you are used to, simply because the slope of this line need not be constant with voltage. In practice, the MOSFET, those of you who have taken, the MOS modeling class, you probably know that as you keep increasing the VDS, the slope of this line, which we nicely assume to be 1 over lambda I, is not really, as constant as you would like it to be. The so-called equivalent small signal resistance of the current source is not constant with voltage. It keeps changing. So, to that extent, stuff will be in error, right? But what else? Assuming the slope was constant, is there still something wrong with the model? So, this one, the GO is nothing but the slope of the current, the I versus V at some point. If you assume the slope is constant, that slope remains constant throughout the saturation region. So, now can you comment on whether this thing is correct, or there is still an offset. Please note that if you plot the IV characteristics of I and GO versus, so this is V and I, how does this look? It is a straight line. Okay, does it pass to the origin? When V is 0, what is I? It's I naught. And then as I go on increasing V, what happens? From I naught there is a slope. Okay, so this is I naught, and this is, so is the model correct or not? Yeah, one crib is that this I and this I naught are not the same, right? Okay, but apart from that, that finite output impedance is definitely a problem. If I make GO infinity, then you know that I'm screwed, right? So, nothing comes out of the DAC. So, I will clarify this in the class, but it turns out that finite output impedance is indeed a problem, and for a given resolution, you can go and figure out how much GO I need per current source to be able to get required DNL and INL. I believe the problem with this analysis is I have just truncated this to 1, so actually if I expand this by I think to another one, then you will certainly get nonlinear terms. So, that is one thing. So, the best way of enhancing output impedance is what? So, this is your original current source. The output impedance here is not good enough. So, what will you do? You will add equivalently, you take this current source and then you pass it through a current controlled current source. A current controlled current source is a contraption which takes in a lousy current and make it look like a great, a current control current source ideally has got 0 input impedance and infinite output impedance, correct? In practice, the easiest current control current source the simplest current control current source that you know is simply a common gate amplifier, and the common gate amplifier basically will take whatever impedance you have looking in here, and the equivalent impedance looking in here is basically this impedance at the source multiplied by approximately GMRO. This is the current control current source. So this will enhance the output impedance of the basic current source by a factor GMRO. And a simple way of deriving these bias voltages is the following. What is the minimum voltage required to keep the lower transistor in saturation? What is the minimum VDS required? It's delta V, which is VGS minus VT. So what is the lowest voltage that you can apply to V cascode? Okay, what is the motivation behind this discussion? The idea is that this will behave like a good current source, but clearly it will behave like a good current source only when the voltage across the current source is greater than some minimum, and the idea is to make the minimum as small as possible. So the question is, if this is V cascode, the lowest this voltage can go before M2 gets into triode is what? V cascade is the potential at the gate. How low can the drain of M2 go before the transistor M2 gets into triode? V cascode minus VT. See, if you have a MOS transistor, the gate is at some voltage. How low can the drain go before the transistor gets into triode? It can go one threshold below the gate. So if the gate potential is V cascode, the lowest potential the drain can go while still keeping M2 in saturation is V cascode minus VT. And why are we interested in keeping M2 in saturation? So when does the common gate behave like a current controlled current source? When the transistor is in, see, you want this guy to be a current controlled current source. This will be a current controlled current source and multiply up this impedance looking in here by GMRO only when this guy is in saturation. So that is why you are interested in keeping M2 in saturation. And if you want to keep M2 in saturation, you want to make sure that the drain is at least at a potential V cascode minus VT, and that becomes the minimum VDS you require to make this operate like a current source. And and you want this minimum voltage to be as small as possible, so that even for a small voltage across the current source, the so-called current source, it behaves like one. If this is V cascode minus, if the gate potential is V cascode, what is the source potential here? V cascode delta V plus VT. The source potential is nothing but the gate potential minus the gate source voltage. The gate source voltage is, assuming it's carrying a current I which corresponds to an overdrive of delta V, is delta V plus VT. So the source potential is V cascode minus VT plus delta V. Now how high must this be before, to ensure that M1 is in saturation? Delta V plus VT. If the gate potential is delta V plus VT, how low can the drain go below the gate and still keep M1 in saturation? It is delta V. So V cascode minus delta V plus VT should be at least delta V to ensure that M1 is in saturation. And why are we interested in keeping M1 in saturation? Let me quickly go over this. Assume the transistor is in saturation, right? So this is some VG and this is VD, alright, some is carrying a current I, and this transistor has got a transconductance GM and an output resistance RO. The idea I'm trying to, instead of rather than working it out, I'm trying to give you some intuition about why this impedance gets multiplied. So if I yank this up by delta V, what happens to this voltage? It goes up by delta V. Okay. So if there is a finite RO, how much does the source voltage go up by? If there is a finite output resistance, this source voltage changes by GMRO divided by GMRO plus 1 times delta V. Okay, now before I go further, if RO is infinity, why is delta V 0? Why is the change here 0? The current flowing through the transistor is a constant. So the current flowing is a constant and RO is 0. RO is infinity. If RO is infinity, what does it mean? It means that the current is only dependent on VGS. It's not dependent on VDS. So if the current is only dependent on VGS, if I change VG, the VGS must remain the same if it is carrying a constant current, which is true here because there is a current source in the source. So if this goes up by delta V, the VGS must be the same, so this must go up exactly by delta V. Okay. Now what happens if there is finite output resistance? Can you physically justify GMRO by GMRO plus 1? Of course, one thing is that you can replace every transistor here by the incremental equivalent circuit and you do the math, and yes, you will get GMRO by GMRO plus 1. Okay, so is there more to it than meets the eye? If I keep this fixed and yank this up by delta V, what happens to the source potential? Okay, if RO is infinite, if I yank the drain up by delta V, what happens to the source potential? It shouldn't change, correct? Because the current shouldn't depend on VDS. So, however, if the resistance is finite, output resistance is finite, then what happens to the source potential? Yes. If I yank VD up and there is finite output resistance, what will happen? More current will tend to flow through the transistor. So if more current flows through the transistor compared to the current source, what happens? This node potential will go up. Okay, and that will go and crush the gate source voltage. Okay, bringing the current back to I. Okay, and since the GMRO device is an index of how much more influence the gate source voltage has on the drain current when compared to the drain source voltage. The drain current is influenced by both VDS as well as VGS. Okay, but the influence of each of these guys is different. The VGS in principle is supposed to influence the drain current to a much larger degree than VDS. So that GMRO is some kind of the number which quantifies that. That's all. So if I yank this up by delta V, so what is the exact change in the voltage? What is the change in the voltage in the source? It should change by a small amount, and it turns out that is delta V times 1 by 1 plus GMR. So if I yank this voltage up by delta V, this moves only by a small amount. Okay. Now if this current source had a finite output resistance RO, let me call this R. If I yank this up by delta V, this changes only by delta V divided by 1 plus GMRO. Okay. So what is the voltage change across this R? It is this character here. So what is the increase in current here? It is nothing but delta V divided by 1 plus GMRO by R. So, and where must that current flow? It must flow through this transistor and come out. So if I yank this up by delta V, the change in current is delta V divided by 1 plus GMRO times R, which basically means that the equivalent output impedance is approximately GMRO times R. So this is how a cascode, this is one way of understanding, why a cascode does better than just a single transistor. Of course, you should also, plop down the equivalent circuit and do the math, and you should be able to get the same result. You'll be off by +1 and all this other stuff, but typically GMRO is a large number, so this is a reasonable estimate of what happens. So if V cascode in this diagram, if V cascode minus Vt plus delta V should be equal to delta V, right? Because that is the minimum voltage required to keep M1 in saturation. Then what should V cascode be in terms of delta V and Vt? What is this? It should be 2 delta V plus Vt. Okay, at least. How will you generate Vt plus 2 delta V? Okay, how will I generate Vt plus delta V? I mean, this is if these two transistor sizes are the same. This is I. This voltage is Vt plus delta V. I need to get, if I want to generate Vt plus 2 delta V, what do I want? What would I want to do? Okay, if I took a transistor and reduced its size and push the same current into the transistor, what happens? The MOSFET is a square law device where the current depends on the square of the overdrive. So if you want twice the overdrive, what I should do is take I and pump it through a transistor of size x by 4, and that will give me Vt plus, in which case the lowest potential that this can go to before the top transistor gets in the triode region is